Assalamualaikum, one and all. Welcome back to Sir K Loves Physics and Chemistry tutorial for high school students. This episode is a revised edition of a past upload on RL circuits. We will focus on computing the rates of increase in current at time equals 0 and at a specific time before the final steady current is achieved in the inductor. So just sit back, relax, watch and learn. The question is, an inductor with an inductance of 2.50 Henry and a resistance of 8.00 ohms is connected to the terminals of a battery with an EMF of 6.00 volts and negligible internal resistance. Question letter A, find the initial rate of increase of current in the circuit. Question letter B, find the rate of increase of current at the instant when the current is 0.500 amperes. Letter C, find the current 0.250 seconds after the circuit is closed. And question letter D, find the final steady state current. As shown in this circuit diagram, we have the resistor big R and the inductor big L connected in series to a source of EMF such as a battery. So we are given the amount of the inductance, capital L, equal to 2.50 Henry, and the amount of the resistance, big R, equals 8.00 ohms, as well as the amount of the EMF in the battery, epsilon, equals 6.00 volts. So our first target variable is the rate of increase in the current denoted by di over dt, which can easily be computed by just dividing the amount of EMF epsilon by the amount of inductance, capital L. And secondly, we also want to determine the rate of increase in the current, all right, at a time when the amount of current is given, right, equal to 0.500 amperes. So that will require us to use this formula. di over dt equals quantity EMF minus the current I multiplied by the resistance, big R, all right, to be divided by the inductance, capital L. And for letter C, our target variable is the amount of the instantaneous current, small letter I, at a given time equal to 0.250 seconds. And that would require using this formula. Okay, instantaneous current I is equal to the EMF epsilon divided by the resistance, big R, times the quantity 1 minus Euler's number raised to the power negative R over L times the time t. And lastly, we are also asked to find the final steady current, capital I, which is simply the amount of the EMF epsilon divided by the amount of the resistance big R. We use the equation that relates the EMF epsilon, the product of the inductance and the rate of increase in the current, or that is, epsilon equals negative capital L times delta I over delta T. As shown in the circuit diagram, the potential difference across the resistor big R depends on the current passing through the resistor, whereas the potential difference across the inductor depends on the rate of change of the current. So the inductor actually slows the growth of the current when the circuit is already completed, right? The increasing current through the inductor induces a negative EMF. That is why there is a negative sign in this equation. That is in accordance with Lenz's law of electromagnetic induction. So to compute the inertial rate of increase in the current at time equals 0, we just get the value of the EMF divided by the amount of the inductance, capital L. That is, di over dt equals 6.00 volts. That's the value of the EMF divided by 2.50 Henry, which is the given inductance. All right? So when we simplify, we get the value of the rate of increase in the current at time equals 0. That is equal to positive 2.40 amperes per second. It is positive since initially the current is increasing positively. And for the unknown variable in question letter B, all right, we are looking for the rate of change in the current, that is di over dt, all right, at the instant when the current in the inductor equals 0.500 amperes. So this is the formula that we will use. All right, di over dt is just equal to quantity epsilon minus the product small letter I times big R. All right, and that will be divided by the inductance, capital L. So substituting the given values into this formula, we get quantity 6.00 volts minus 0.500 amperes times 8.00 ohms. All right, so the values inside the bracket is to be divided by the amount of the inductance, capital L, which is 2.50 Henry. All right, so when you do our math, we get the value of the rate of increase in the current, di over dt, all right, equal to positive 0.800 amperes per second. Notice that at this instant, the rate of increase in the current is, as expected, less than the rate of increase in the current at time equals 0. Moving on to question letter C, before we can find the current small letter I at time equals 0.250 seconds after completing the circuit, we first find the power of the Euler's number big R over L times the time t, right? So substituting, we have the value of the resistance big R, 8.00 ohms, and that is to be divided by the given inductance 2.50 Henry, all right? So the quotient will be multiplied by the time small letter t equal to 0.250 seconds, all right? So the result is, after dividing and multiplying these values, we will get 0.800, all right? So that means the power of the Euler's number is negative 0.800, which we can already substitute, all right? Uh, that means the Euler's number with its power negative R over L times T, right, is equal to the Euler's number raised to the power negative 0.800. So with the help of your calculator, the value of the Euler's number, of course, is 2.718, and that is to be raised to the power negative 0.800. Finally, we get the value equal to 0.449, right? So, we can now continue computing the current small letter I, all right, based on this equation. So that is small letter I equals the EMF, which is 6.00 volt, divided by the value of the big R, 8.00 ohms. And that is to be multiplied by quantity 1 minus 0.449. So again, doing our math, we will find the value of the current I, all right, at time 0.250 seconds. So the instantaneous current, small letter I, is equal to 0.413 amperes in three significant figures. Finally, for question letter D, the value of the final steady current capital I, all right, we just use the formula. Capital I equals the EMF divided by the resistance big R, that is 6.00 volts divided by 8.00 ohms. So we get the final steady current capital I equals 0.750 amperes in three significant figures. So this same current, big I, is the current that passes through the resistor, big R, right? While in the case of the inductor, the rate of increase in the current, all right, through this inductor is actually depicted in this current versus time graph, right? So earlier we already computed for the initial change in the current, all right? That is at time equals 0. And we are also able to determine the instantaneous current, all right, at a given time of 0.250 seconds. So, as the curve suggests, its slope is getting smaller and smaller, all right, suggesting that the rate of increase in the current is getting lower and lower until it reaches, all right, a certain value of the current, all right, that is equal to the final steady current, capital I, which you just computed as equal to 0.750 amperes, right? And at a certain time, which we call the time constant, denoted by the Greek letter tau, all right, at that point in time, where the time constant tau is just equal to the ratio of the inductance capital L over the resistance big R, all right? That is the formula for getting the time constant uh, in an inductor resistor series circuit such as this, all right? So at that point in time, we may also determine mathematically the amount of the instantaneous current, small letter I, using the formula small I is equal to the product of the maximum current or final steady current by the quantity 1 minus the reciprocal of the Euler's number. So this graph of current versus time, okay, which suggests a what we call a decreasing rate, right? A decreasing amount of the rate of increase in the current, all right, is commonly known as the growth current in an inductor resistor series circuit such as what we are discussing here now. So that's it. We are done with our tutorial for this topic. Till the next episode, mabuhay, Masya Allah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.